Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.
Last week I explained what we get from Einstein's theory of special relativity. That is what we observe for things moving near the speed of light. What we see near the speed of light goes very much against our common sense that we get from living our lives at much slower speeds. You see strange things like clocks slowing down when they move. For those of you who weren't here last week, don't fear, there will be a review. And for those of you who were here, you may remember that I said that special relativity is crucial to us in astrophysics. This is because there's quite a bit of energy out there in the skies, and there's many things in space that move quite fast. There are even large flows of material moving near the speed of light. So this week I'm actually going to show examples of this, that these tricks that special relativity place the light that we see. This is not going to be an exhaustive listing. For starters, if I did that, it would take a very, very long time to go through every single object. And for another thing, there wouldn't be much to talk about next week. So what I will do is show some examples that demonstrate how relativity skews what we see from the skies. So game plan for today is that I'm going to review what we mean by special relativity and these basic results that I talked about last time. And then we'll take a closer look at what this does to light. We'll go beyond the basic results of special relativity and see how it affects wavelength. Light has a property called wavelength, the number of times you see a cycle of it per second, and that is strongly affected by special relativity. The way that it's affected allows us to use special relativity effects as a basic tool in astronomy. I'll also discuss how special relativistic effects brightens or dims sources in the skies. And at the end, how special relativity is crucial to interpret relativistic flows, such as very fast jets. So this is what we discussed last time. This is the theory of special relativity. It's two relatively simple statements that together have some pretty profound consequences. The first here is a statement of the basic principle of relativity. That is that the laws of physics are the same for any observers that are moving smoothly relative to each other. This means that if you perform an experiment and you were to look at that experiment from another perspective that is moving smoothly with a constant speed relative to that one, you would see the same end result. The example that we showed for this was somebody tossing a ball up and down in their hand. We used a little cart that you could see popped a ball straight up and it fell straight back into the cart. It didn't matter if the cart was sitting still on the table or moving at a constant speed on a rail. It's also the reason why, if you're able to put the cup of coffee down on a table next to you and it won't move here in this auditorium, you can do the exact same thing in an airplane at tens of thousands of feet in the air, moving at hundreds of miles an hour. As long as it's smooth speed, it's got the same physical results. Of course, all bets are off if you have accelerations like turbulence. The second part of special relativity is what really turns our common sense on its head. That is that the speed of light will always be measured to be the same by any observer. Nothing outruns the speed of light as well. This means that it doesn't matter how fast you are moving or how fast a light source is moving towards or away from you, you will always measure the same speed of light. It doesn't matter how fast you are running with a flashlight, the light coming out of that flashlight has the same speed than if you had the flashlight sitting on a table. This is very different from anything else in the universe, like a ball that you might be tossing forward. If you are running as you toss the ball forward, you're going to give a boost to that speed of the ball relative to somebody who sees you who's sitting down and watching this. So to figure out what that does to space and time, we then went through looking at some precise clocks. These are called light clocks. We have some source here that bounces a beam of light up to a mirror and ticks back down. And so you have one speed of light and one length here. You know the tick length. This gives a very precise tick period for your clock. And you can take any clock and synchronize it to this light clock. Therefore, what we're going to see doesn't just go for light, but it goes for any measurement of time. And the reason we use light clocks is because you can easily see how time stretches when a source moves. If you watch, you notice that the red clock caught that light before the blue clock did. This is because, as far as from the red clock's perspective, all that it is doing is sending that light straight up and it comes straight back down. That means that it has a short path here for the red tick. The blue clock, relative to the red clock, is moving off to the side. Therefore, it has to shoot that light up at an angle in order to catch it with the mirror and be bounced back down. This is going to be a longer path, and therefore the tick from the blue clock, as far as the red clock is concerned, has to be longer because the speed of light is going to be the same. Of course, as far as the blue clock is concerned, it is sitting still. It's just sending the light straight up and down. It's got that same tick path here. The red clock is moving off to the side there. So the blue's ticks are just the part that's going straight up and down to itself from its own perspective where it's sitting still. Therefore, when it's sitting still, it thinks it has a shorter tick going up and down here than the red clock thinks that it had going up there. This also works the other way around. As far as the blue clock is concerned, the red clock is moving and the red clock is running slow. That led to some even stranger results, where I showed that you need some uncommon sense to deal with this constant speed of light. I just discussed how this required time to dilate. That was what we mean by clocks slowing down when they move. It's an effect called time dilation. So you've stretched out the ticks of the moving clock. It also requires your length to contract when you see for an object that's moving. This we demonstrated with the example of an asteroid out in space, and you are measuring its length with two light clocks. One of them is the blue light clock, and it's attached to the point of view where the asteroid is sitting still. The other one is an orange light clock. At this moment here is exactly coincident with the blue light clock, so it's about to pass it. And from that one is moving relative to the asteroid. From its point of view, it is sitting still and the asteroid is moving. If it's moving fast enough, you will see that it would take, with a path over here for light, for the orange light clock, 4 orange ticks as far as the blue light clock is concerned, but 5 blue ticks. So you have one speed that, as far as the blue light clock is concerned, the orange light clock is moving at this particular speed past the asteroid. And it took 5 light clock ticks. From the orange perspective, the asteroid moved past it, but it only took 4 light clock ticks. These have the same height. Therefore, as far as each is concerned, when it's sitting still, that's that same original sitting still tick. So with less ticks from the orange point of view, that asteroid actually is shorter from the orange's perspective than from the blue's. It's shorter by a certain stretch factor. And that stretch factor depends only on the speed between the object and the observer. This is the only piece of math I'm really going to bring up today. This is the stretch factor for time and space in special relativity. We call it gamma. And you can see that it's got on the denominator here a value that is very close to 1 if your speed is very, very small compared to the speed of light. So this is why we don't notice it in everyday life. The stretch factor for time and for space is pretty much non-existent. It just looks normal, as if there's no stretching. When you get near the speed of light, you can see that this over here is going to get small, and therefore the stretch factor is going to get very, very large. So this should be very strange. It doesn't act anything like what we normally expect. So I'm going to step back from that for a moment and go on to something a little bit more concrete for us to deal with wavelength. And so we're going to deal with things that we might all be able to understand from our own personal life. And this is sound. We have a conductor who wants to tune up the orchestra. And what he has are 2 saxophones over here. Each saxophone is going to be emitting a sound. And that sound is carried by the air. Now, a property of waves that are carried by a medium here, in this case sound is carried by air, is that the sound, the wave, has a speed relative to the medium. So if you have still air here, you're going to have the same speed of the sound coming from this guy as coming from this one who's moving through the air. So what is happening here is that I'm going to be marking the peak of the waves of sound coming out of this one and coming out of that one. As this one moves across this way, it's emitting a peak of the wave of sound. So after a step, you've got a complete wave, and over here it's gone not that far. It started from over here with the guy that was moving in the air, and therefore it's gotten equally far here. However, the saxophone is caught up part of the way as it emits the next peak of wave. The peak of wave from this one, the wave of sound, starts out here. The wave of sound from this guy starts out here. So in the next step, you'll see how, again, that first one has gotten just as far, but that second one gets squashed up a bit as this guy catches up. And again, he emits another one and partway catches up. And again. Now what's happening is I've made the saxophone move at half the speed of sound because he's gone 2 waves worth of distance, while 4 waves worth of distance has gone by there. And what's happening is that the sound piles up. There's the property of the sound called frequency is how many times you see a wave per unit time, like per second. And you can see there's going to be twice as many waves per second coming at the conductor from this one as coming from at the conductor from the one who's sitting still in the air. So with half the wavelength here, it's got twice the frequency. And how we experience frequency with sound is by the pitch. This means it has a higher pitched sound coming from the saxophone that's moving toward the conductor. So here's a second way of looking at it. We now have 2 conductors. We have one saxophone sitting still in the air. And we're going to have one of the conductors move through the air towards the saxophone. He's going to move at half the speed of sound. We're going to count how many waves pass completely each conductor. So over here, this first wavelength has just barely reached, it hasn't quite passed either one, so you've got their counters at 0. So after 1 wave period, that first one has passed this conductor here, and this guy has not only had this one pass it, he's also moved forward and therefore passed by that second one. In the second step, 2 have passed by that guy, and this guy is not quite caught up with the 4th, so only 3 have passed by. So now we end up with 5 and 3, and then 6 and 4. We begin to see a pattern emerging. What happens is that the moving conductor here, who is checking the tune of this saxophone, has seen 3 waves of sound that he has passed, beating into the waves there, for every 2 waves of sound seen by the resting conductor over here. That means that he's seeing the sound with 1.5 times the frequency that that guy is seeing. Once again, the sound is piling up, although it did matter whether it was the source of the sound that was moving or the conductor who was moving towards the source. So this effect also works if you move away from the sound. I've just shown here if you were to have started and sent out sound in a circle, how you would have piled them up on the side and stretched it out to the back. That means you have a longer wavelength and a lower frequency, so a lower pitch. This is a perfectly classical effect. It's perfectly normal in our everyday life, and I'm going to prove that to you with this item over here. What I have here is the world's most annoying whistle. It's specially designed for physics lecture halls. So everybody can hear that. You pretty much can't hear anything else when it's on. So what's going to happen is I'm going to spin it, and I'm going to move it so it's going to be going forward and back relative to you. And you'll be able to hear the pitch getting even more shrill and high pitch, and it getting a little lower pitch as it moves away from you. That should have been pretty obvious, I think. This is not just an effect of having the sound source moving at all. It has to move forward and away relative to you. And therefore, I'm going to show this by, again, moving it, but no longer forward and away like that, but rather up and down in a circle. And I'm going to walk across the room. And as I walk, at some point, I'll be directly in front of you. And at that point, you shouldn't be hearing the Doppler effect slightly from the side, which you might get if I'm over there and you're over here. But at that point, you should almost not hear it when I'm in front of you. It's a little hard to do. How can I say? I was never a baton twirler in childhood. And just for comparison, that should have been much more muffled than this. Okay. So that's the effect that we hear when you hear the change in a train's whistle when it's passing by you and so on. It's a perfectly normal thing in everyday life. The trouble is that we see a similar effect with light, but it doesn't quite work in the same way. This is because this is a classical prediction. It's for waves that move in a medium. They have a speed relative to a medium. The trouble is that light doesn't have a medium that carries it. People thought it did, and they gave it a name. They called it the ether. Scientists did very careful experiments to see the difference between a light source moving towards you moving towards a light source, these sorts of effects you would see with sound. And there simply is no such thing. Light has a speed relative to the observer, but not relative to a medium. Therefore, as you can imagine, what matters is the speed with respect that an observer moves relative to the source, and the source moves relative to the observer. So when you go to calculate this wavelength effect, you do indeed see waves stretch out, waves of light stretch out if you and the source are moving apart from each other. And the waves do indeed pile up if you and the source are moving together. This comes from depositing waves, so to speak, as the source moves, like we saw in the case of the sound. The wavelengths start at different points as the saxophone moved along. But you also have to keep track of the relativistic effects. Time, the rate at which time is moving is different from the point of view of the source, which is sitting still, and the observer, which sees the source of light moving. You also have to keep track of such things as the contraction of length when you've got something moving, so how close the two objects appear to be. When you go through the math, and this is the kind of thing that undergraduates in physics spend their weekends doing, but we won't, so you'll just have to trust me here, you get a similar effect to the Doppler effect for sound. The details are slightly different. All it depends on is the relative speed between the observer and the light source. You don't have a difference like with the conductor and the orchestra where you saw it. Sometimes it was twice the frequency, sometimes it was 1.5, depending upon who was doing the moving. So to show what this would look like, I've drawn out here the visible light range of the spectrum. So what we have here is the colors of light spread out. And I've got a scale here in units of billionths of a meter. So a meter is about yay big. So we see light that is purple is about 400 billionths of a meter. We see light that is red about 700 billionths of a meter long in terms of the wavelength of light. If you go further to the red than red, you go through the infrared off to the radio. If you go further to the violet than violet, you go through higher energies like the ultraviolet to the X-ray, gamma rays, and beyond. The formula for what happens with light, for the Doppler effect, is a fractional effect on your wavelength. This means that it will shift by a certain percentage. It could be 1%, 10%, 50%, depending upon your relative speed with the light source. If you're approaching a light source, the light gets shifted bluer, that's to higher energy. If you're going away from the light source, the light gets shifted redder to lower energy. And the change is usually quantified in terms of putting it in a mathematical formula by the ratio of wavelengths. Wavelength is usually symbolized with this symbol here called lambda. So the wavelength that you, the observer, see over the wavelength that was sent to you from the point of view where the source is sitting still. If you're sitting still relative to each other, that'll be 1. Your difference from 1 is very small at slow speeds. It goes approximately as your speed over the speed of light, which at ordinary speeds is millionths or something like that. What becomes much more extreme is when the speed goes near to the speed of light, and suddenly it gets very large. So what I have here is a diagram of what we might see with an object. This object here has a spectrum. So we'd have, so not seeing equal amounts of these colors. This line is indicating how much of each of the colors in the spectrum this object has. So it gets rather a lot of this yellow here, a little bit of the darker yellow here, and a little bit of the green off to this side. And therefore we see it as this greenish yellow ball. So let's say that we push this ball at 10% of the speed of light away from us. The Doppler effect makes the light shift more towards the red, so we'd see it more as an orange object. And the Doppler effect, if we were to shift this object at 10% of the speed of light towards us, would roughly do this. You would see it as a blue-green object over here. So this would be the same spectrum, the same amount of colors that is coming to us from the object. The other thing that light can do is, rather than having an assortment of colors that it sends to us, you can have light emitted from an object that has a single frequency or wavelength, a single pure tone of color. So I've shown schematically here as saying it would be on this line there, and you'd have no light, and then you would have a single bit of it there. Equivalently, you could also have an object which had an even range of light with all sorts of colors and suddenly have no light there. What usually would produce these things are the basic properties of atoms. Every atom has a certain ability to either emit light or absorb light at certain points in the light spectrum. These form a pattern that we'll be able to recognize across from any source. So what we have over here is a white light over here on the table. Its light is being emitted and sent and reflected over here, where it's being looked at by a special camera. This camera is able to separate out that light into its spectrum, spread out the colors that it's getting from it. That's what we're projecting over here on the screen. We've got an even amount of light here from the blue, green, and red. And what I have here are some glasses which have certain particular atoms in them that are useful to people who want to look at certain types of bright light. If you're able to see here, you'd notice that there's a slight, they're clear with a slight purplish tinge maybe. And if I slip the glass here in front of the spectrum between it and the, yes, you can see that there's some light that's beginning to be missing here between the green and the red and off over that side between the blue and the green. It might be a little easier to see over here if I just put the glass in front of the camera. So you notice there's something in the glass that has specifically taken out the light there and the light there. This pattern comes from the atoms inside the glass, and we would recognize it from the same type of atoms anywhere in the universe. And of course, there are many other types of atoms that take out other very specific pieces of light. So if we had these particular lines coming from an atom, and we knew that we were expecting to see a line here, it would only take about 1/4 of the speed of light to push that line all the way from the center of our visible light range to the edge, to push, say, from green to red over like this. Similarly, it also takes only about 1/4 of the speed of light to push from green here all the way out to violet. And by my calculations, therefore, approximately from out here to out there, or from maize to blue. And you thought I wouldn't work in anything Michigan related today. Now, so as perhaps a more concrete example, let's see if a morning necessity. You really want to get coffee from the ubiquitous coffee company. And if, as you're going off to get your coffee, instead of seeing this, you see something more like this, you know you're in a little bit too much of a rush to get that caffeine fix this morning. So these patterns we recognize in the universe are how we can use relativity as a tool. We call this red shifting and blue shifting light, and from it we can directly recognize a relative speed between us and an object. So we can do searches for things by looking for these relative speeds, by looking for these shifts in the light. So this is schematically what we might be looking at. You have a bright star here and a dark object that's circling it. Well, gravity works both ways. This massive star here is pulling on the object, that pulls it into an orbit. But also, this object here has gravity. It's tugging on the star, so it tugs the star that way as the star tugs this one that way. And this forces the star into an orbit here. Now, the star is bigger, it's heavier, it's therefore harder to move. And that means that the effect here, the orbit, is going to depend upon your mass. It's much easier for the star to give this object a big orbit. So the size of this orbit here is going to be smaller for the star, which is why we normally don't notice these things. It's about the size of the orbit here relative to the size of the orbit here. It goes something like the mass in this object here to the mass in the star. So here it's very exaggerated. You might have an object that's about 1/3 the mass of this star, and you see that it forces that star into a small inner orbit there. Well, this is used for searching for all kinds of objects that circle stars. One of the most interesting of recent years is searching for dark companions that are the extrasolar planets. Those of you who were here last spring, as I understand, there was an entire talk about the searches for extrasolar planets. And I'm just going to go over the basics here. You have a planet that is too faint to see. but it's circling around the parent star here. And the star, there's not two stars here, it's a star at different points in time. Its tug forces the star into a small orbit. For part of its orbit, the star is moving more or less towards us, and we see its light, including all the patterns produced by the atoms, blue shifted. And when it's moving more or less away from us, we see all of its light, including the patterns that are produced by the atoms in it, red shifted. So our typical case, however, these are very small shifts, because this is what we've been able to detect thus far. Our planets whose mass is about 1/1000th of the star mass, so Jupiter-sized relative to our own sun size. They have to be pretty close in to give a big enough tug to produce an orbit like that we can measure. So the period is of order days. And like I said, the size of that star's orbit is going to be much smaller than the size of the planet's orbit. So the size of the planet's orbit is going to be something like 1,000 times the size of the star's orbit. It's got this tiny little wobble back and forth produced by this planet. Now, if we could see light from the planet, you would know that the planet's moving at something like 150 kilometers per second, a pretty respectable speed, although it's still only about a part in 2,000 of the speed of light. You can imagine if you had a very good instrument that was able to spread out the colors of light better than the thing I was showing on the screen before, you might be able to carefully measure the center of any peaks of light or any troughs of light from emission or absorption lines, where light is being produced or taken away by atoms. And if that's the case and you measure it very carefully, you might be able to detect a part in 2,000 shift. But the real problem is that we're not detecting the light from the planet. We're detecting the light from the star. And because the star has a much smaller orbit than the planet, it has the same period, smaller distance to go, so a smaller speed. Instead of looking for a shift of about a part in 2,000, we're looking for a shift of something like a part in 2 million for a line. You can imagine that that would be very difficult to measure. Astronomers, of course, have an answer to that, and that is to use a whole bunch of lines. Now, what I have here is actually the spectrum for our sun. And unlike this over here, it starts at the very far red. You move across a strip here, and when you reach that end, you go back to another strip. So this is actually stacked up strips. You go through the spectrum like so. You can take it apart, tape them together, and make one long spectrum of the red all the way through to the violet that would go all the way around the room, or maybe more. So each bit here corresponds to a different wavelength of light, starting from the far red through the green to the blue to the purple. And you can see that there's a whole bunch of places where there's light that has been taken out, just like I did with the atoms in those glasses on the spectrum over there before. So this is fairly typical. This is our sun's spectrum. It has literally thousands of lines. So if you look at another star like our sun, it should have a pattern of thousands of lines. And while you might not be certain that this line over here has shifted by a part in 2 million, if you know that it's shifted a certain way, that line here, and that line there, and that line there, and that line there, and so on, have all got to have shifted in the same way. You can attempt to see, if you don't know for sure, it looks like it might have shifted a little, you can get more and more certain the more that you look at it, and if you see the same very small effect. So you get more certain of the pattern shift by having a whole bunch of lines instead of one. So this was a fantastic result of recent years. And it's been the most successful discovery method, by the way, for extrasolar planets. About 130 planets have been discovered through this method. What is interesting about this, from our point of view this morning, is that special relativity is the smallest part of this. It is so banal, so ordinary in the lives of astronomers, that it's simply used as a tool. We see a shift in light wavelength, and we know there's a relative speed between us and the source. And we can use that to find all sorts of things. So you probably want something a little bit more dramatic this morning. So I'm going to introduce you to an object called the lawn sprinkler. It has a much less dramatic name, SS433. But what it is an object that at regular light looks like a bright star. But it's also a radio source with a funny shape and an X-ray source. You can guess there's a lot of energy in this because it's producing X-rays, and X-rays are very energetic. Well, this object is nice for us to look at because it's pretty much in our backyard as far as astronomers are concerned. It's only 16,000 light years away, which for us would take very far to get there, but like I said, there aren't that many objects like it, so this is nice and nearby. It was first noticed that it had a very bright spectrum, and it had some oddness to it. There are periodic changes in the spectrum. The lines were shifting. This is just like the planet case. It tells you that there's something going on that's tugging at the star, that we couldn't see this other object. There was a dark companion. It's called a binary star, where you have one star orbiting another. This effect was much larger, by the way, than what we see for extrasolar planets. What powers the X-ray and the radio is the fact that there are jets being pushed off very powerfully. From the amount of radio and X-ray, they can tell that the jets use the power of about 100,000 suns. So what is happening, this is just a drawing here, is you have a bright star. I'm really trying to get this to work. Bright star sends some matter onto this dark companion, which pushes off very powerful jets. The jets have a hard time staying stable, so they kind of wobble back and forth here. They wobble back and forth, so sometimes they're pushing off some of the jet this way, and other times they're pushing some of the jet off that way. So up like that, down like that. You end up with this little corkscrew effect. It looks like a lawn sprinkler. And you end up with a lot of energy in the X-rays and the radio. So when people took a closer look at this is, like we saw before, we've spread out the light. It's another way of looking at a spectrum. So we have here is a brightness spread out in a color, but this color isn't a color that we see with our eyes. What is an X-ray color. We have here is the wavelengths in the X-ray. Instead of being hundreds of billionths of a meter, like what our eyes see, these are tenths of billionths of a meter out over here. And this is just a subset of the pattern formed by the light of this object. What people would have looked at, seeing this, and say, okay, you have an energetic object, that means you can get emission from heavy material like iron. We should see an iron line over here. Well, this gray stuff is the amount of light they see, and there's no special line right where the iron ought to be. Instead, they see a line that looks suspiciously like the iron over here at smaller wavelengths, that means more energetic, and another line that looks suspiciously like iron over this side, which is at longer wavelengths, therefore less energetic. What they are seeing is split lines, is both blue shifted and red shifted from this object. The object is both coming and going. This is the sign that they have the two jets, one coming towards us with a bright line and one going away from us with a faint line. And this, by the way, is a very big split. It says that the jets are moving at about 27% of the speed of light. That's why it takes about 100,000 suns to power the jet. So even bigger than this, you can see stuff like this in other galaxies. This over here is a picture of the M87 galaxy, which is a big blob of stars over here. This is what we see if you look with our ordinary light, with ordinary telescopes. If we were to take another look at this, what we now have is that big blob of stars is more or less like this. We're just looking at a corner of it. We've got a bright center of the galaxy. We've added to the regular light a bit of ultraviolet light. So somebody took a look with a picture with ultraviolet light, which is more energetic light. That's why we get sunburn by it. And anything that's bluish has ultraviolet. They were able to see, brighter than the stars, was this jet here. This jet is about 5,000 light years long. And it takes a lot of power to push that jet out from the center of the galaxy. There's the power of literally billions of suns going into pushing this jet. There is another jet on the other side going away from us, which is much less bright. People also were able to do studies of the center here. It looks like there's stuff spiraling around the center, which is evidence for a black hole. So the question then becomes, where do we get all that energy for these jets? As I said, the small version, this lawn sprinkler object in the backyard of our galaxy, takes about 100,000 times the power of our sun to push out its jets. A galaxy-sized version, a relatively small galaxy-sized version like the M87 galaxy, takes billions of suns worth to produce a jet. It can get even more energetic. It can take up to 100,000 billion suns worth of energy to push some of the really powerful jets that we see in the universe. Well, the fact that we saw evidence for a black hole in the galaxy with the spiraling matter is a clue for us. It tells us that maybe we should consider gravity as a source for energy. Why? Because gravity is a really good energy source. It makes stuff like this. It makes stuff fall and gives them energy when it goes and hits something. This is a crater created by a meteor in Arizona. What happens for an object like this, a bit less crater-like. What you have is that you have a stream of material that is falling onto some central object. A lot of material falls in. If If you have a very compact, very heavy center, the more you fall towards something heavy, the more energy you get, the more you speed up. So if you get closer to a big mass, you get more energy. So if you get really close to a star, you would get a lot of energy. If you could take that star and you could squash it, so you had the same amount of material, you would then, and you fall even closer therefore, since you have a squash star, you get even more energy. That's why a black hole is really good. Black holes they effectively act like material compressed so far that the force of gravity at them is too strong for even light to escape if you get too close. So you get an awful lot of energy from falling if you fall towards a black hole at the center, if there is a black hole. The energy you get from falling is huge. Einstein's theory of special relativity has as a result that the energy in an object goes as something like mc squared. And that is just from your own material. And that's a huge reservoir of energy. The energy you get from falling is actually comparable to that amount of energy if you're falling onto a black hole. Something like 1/6 to 1/2 of that energy is available from falling. So you can transfer that energy in the material in this disk, and some small part of it can spiral in and almost but not quite hit the central mass, and by that get flung out with a lot of energy, and that's what powers the jets. They think that about 10% of that mass energy that falls onto an object like that can be used to power a jet. So, how much energy do we actually get from material? How much material do we need here? Well, I'd like you to consider a small object, a quarter here. A quarter weighs a very small amount, a few grams, or in units everyone here might understand, a small fraction of an ounce. How much energy does you think that it has? Could it power the United States if you converted a quarter completely into its energy from mc squared for seconds, minutes, days, or a year? Does anyone want to venture a guess? I heard a year. We're not quite that much of an energy hog in the United States. The answer is actually minutes. That is still an impressive amount of energy. We do use up a lot of power. If you could convert a quarter completely into its own energy, it would be a truly terrifying object. It would be a powerful, horrendous device with more energy than a small nuclear weapon. So that means that we can easily use material to feed the beast that pushes out these jets. The amount of energy needed for these small-scale jet objects, like that lawn sprinkler object, needs about 1/billionth of a star per year. So you could take a star and feed this object for about 1 billion years, and it would be able to produce a jet, if you could convert all of that material into the energy that powers the jet. Galaxy-scale jets need more. They need about a star per 1,000 years to about a star per year. So that converts into energy to power the jets. And that is where we get something as powerful as this from. So we have a pile of energy. I mentioned that the galaxy, M87, had a faint jet off to the other side and a bright jet. Also, the lawn sprinkler object had one bright iron line coming towards us and a faint iron line going away. With all that energy, why in the world does one of the jets look faint? For this, we're going to consider 2 light sources. And we're going to consider, well, actually, we're going to consider 1 light source and 2 perspectives on it. One perspective we're going to call the source frame. This is the point of view where the light source is sitting still. One point of view we're going to call an observer frame. This is from somebody who happens to be moving relative to the light source and therefore sees the light source as moving off to the side. I'm just going to show it schematically here with an arrow. So at some time, the light source decides that it's time to let off some light. It hasn't done it yet. It's going to send off some photons up and down. But these photons, up and down from the source's perspective, have to be pushed forward from the observer's perspective. It's sort of like if you were tossing a ball up in the air and running. Someone who was sitting down and watching you run would not only see the ball go up in the air, it would see the ball continue to move with you. So the light gets concentrated forward, and that has some pretty profound effects on the power that we see from light. Now, the brightness that we see for a light source is set by its power, which is a physical concept which just means how much energy are we talking about per time. So how much energy do we receive every single second from something like that light? So the power sets the brightness. And right here we have one perspective on a light source. It's shown here with an X. From the point of view of the light source, it's sitting still, and an observer way off to the side here is coming fast at it. But it is happily emitting light in all directions. It's emitting the same amount of light, same wavelength, same amount of photons per time, so same power in all directions. I'm showing that schematically with a circle here. Well, since we're going to deal with energy per unit time, when we change perspectives, we change our point of view, we have to keep track of relativistic effects here. There's the time the photons leave this light source relative to the time that the photons get to us. There's the amount of energy emitted in each photon. And with red shifting and blue shifting of light, red shifting of light gives us less energy per particle of light. Blue shifting of light gives us more energy per particle of light. And so there's the, there's the angle effects, there's the energy effects, and there's the arrival time effects. And you put that all together, you do a bunch of math, you get the power observed from the point of view where it's the light source that is moving off in this direction is shown schematically this way. There is a lot of power coming directly at anyone who is looking at the object moving directly towards them. There's almost no power left from the back end that sees the light source moving away. You might say that part of it is the redshift kind of effect. You see the power greatly boosted and blue shifted over when you're looking down at the jet, and the power greatly redshifted and fainter when you're looking from the back side of the jet. So you have two jets going off in opposite directions. One of them you might be looking at more or less it's coming towards you. So you might see it from here, and you see it pretty blue shifted. When the other one going off in the opposite direction, you're looking at it from this point of view. It's pretty red shifted, so pretty faint. So relativistic sources can hide their light by pushing it forward. This seriously affects what we can observe in the universe. So to start out with, we can take advantage of the fact that we do indeed have a bright jet. We're back looking at this jet from the M87 galaxy. Now we're just seeing that jet bit that previously you saw coming off like a ray from the bunch of light. They've taken in a zoomed in look here. It's not just a smooth jet of material. We actually have our turbulent features, and there's a series of time-lapse photography from the Hubble Space Telescope in this regular kind of light. This one is so close we see the jet in regular light. Normally we have to look at it in radio light. But in any case, what you have here are pictures taken from 1994 through 1998. And you see the blobs move along. This one is moving along like that. That one is moving along like that. If you take a look here, this one appears to have started out around here and appears to have gotten all the way out to here. And the line here is saying that as far away as the M87 galaxy is, that should be a distance of 24 light years. But it only took it about 4 or 5 years to do that. It looks like this jet is pushing material off faster than the light can even get. And you should all be a little bit upset at this point, because I've just spent a good chunk of last week and a good chunk of this week explaining that nothing goes faster than the speed of light. I'm going to explain this. This is actually a special relativity effect. It was predicted before it was observed as a consequence of special relativity. Back in the 1960s, someone said, hey, relativity can produce an optical illusion that makes things look like it's going faster than the speed of light. In the 1970s, people first started to observe objects. They were able to see things sensitively enough to note this was true. It's not just that M87 galaxy. If we had just one object, we might think we'd made a mistake. Here's an object that's a very bright, active galaxy. It's got a funny name with a bunch of letters and numbers. It's normal in astronomy. What it is called is a quasar. It means it's a strong radio source. It's a galaxy with a big radio source at the center, and it's very variable. It's got a bright radio core here. Within the radio, the core is so bright that you don't see any of the stars around it. All you see is the core of the galaxy, and it sends off these naughty jets. And you see from about, 1992 to 1998, so about 6 years, 7 years here, this blob out here has moved out from about 50 light years from the central core out to about 80 light years from the central core. So again, it looks like it's moving faster than light could possibly go in that 6 or 7 years. We don't just see it in other galaxies. This is an object in our galaxy, so in our backyard, so to speak. It's another object like the lawn sprinkler, which has very fast jets. Because it has these fast jets, it looks a bit like a quasar, so they call it a microquasar. And On March 18, 1994, it had a very bright outflow, blobs going along its two jets. By April 16th, they were able to measure the position in this time-lapse photo between this yellow dot that's the center of the object and where the two blobs had gotten to. And these dashes here show almost exactly the distance light would be able to travel straight across the sky from that point out that way and that way. So again, one of the blobs, the fainter one, appears to be behaving itself. It's gone less far than light ought to have been able to. But one of the blobs appears to have outrun how far light could go. So I said I was going to explain this. And the thing is that relativity takes optical illusions to a whole new level. What we have here is our perspective as being observers way off to the side. There's a mysterious blue object that is moving not quite directly towards us, slightly across the sky and mostly towards us. We're going to imagine that this bright blue object, this mysterious blue object, is going to let off light periodically. Light is going to have to travel along lines parallel to this to reach us, because we're very far over here, actually. So at some point, it's going to let off a piece of light here, a flash of light here, and a flash of light there. So we start our object. It's moving near the speed of light. And what happens at this step is that the object has moved off along its path, and the light has moved along its path. It's hard to tell yet, but the light has actually moved further along here than the object has moved along there. Not by much, but by a little. However, they don't appear to have gotten very far apart. So the next point where we have another light flash, and this light flash will follow this path to us. You can see that the light is moving further along this path here by that much than the object has been moving along its path. We take another step, and the second flash of light starts to move towards us. We get a third flash of light. So what we have here now is that it looks to us over here, since we just see angles in the sky, the object moved from here with this flash of light out to there with this flash of light. And the flashes of light, because light has the same speed no matter how fast the source is moving, they bunch up together here. This train of light flashes will arrive at us, the observer. So we'll first see this flash of light, then a little time later we'll see this flash of light, and then we'll see that flash of light. That's not actually related to the amount of time it took the object and the light to get from here to there. So it looks like this is the apparent time the object traveled. And here's the apparent distance the object traveled. And I would say to you, if you really had an object that got that far, when the light from that object from this point only got that far, you would have something moving faster than the speed of light. But nothing like that has happened here. It's an illusion. It only appears to have covered more distance. The actual distance traveled by the light is this far, and the actual distance traveled by the object is this far. And that is what we are seeing in all of those jets. The jet coming towards us gets this optical illusion and appears to be traveling faster than light. So I'm going to finish up with a little taste of things to come next time. What I have here is an image in radio light. The reason why it's taken in radio light is the way that radio telescopes are constructed allow you to get very fine resolution on the sky. This little arrow here shows us about 1/billionth part of a circle. It's a very, very small angle. If you can see down to this size, you're able to see something that's about 2 meters across on the surface of the moon. And they're actually able to see down even finer than that. As you can see, there's objects and bits here that appear to be smaller than that. They have a scale marked here that's called 1 parsec. A parsec is a unit used by astronomers that's about 3 light years. So this object here, since it's considerably bigger than this, is definitely light years across. Well, this is light that we're seeing in the radio after an event which happened, and therefore the start of the thing, apparently, it's named by the date over here. It's an event that happened on the 29th of March, 2003. The picture was taken on the 22nd of April, 2003, less than a month later. So this object appears to be about 1 month old and to be light years across. Just like those relativistic jets before, you can expect this is an optical illusion. We have a very relativistic object here. This is called the afterglow light of a gamma ray burst event. These are indeed very relativistic sources. There's a lot of special relativity that goes into interpreting these things. They'll be the focus of my talk next week. So finally, I'd just like to wrap up with a little review of what we may have seen here. I took you on a tour of the warped view that we see of the skies due to special relativity. I showed you how the velocity between you and a light source will shift the color of the light that you see, and how we can use that as a basic tool in astronomy to determine speeds and therefore many things about hidden objects that are affecting speeds. I showed you how fast sources can hide their light by beaming it forward. So it makes a difference to us whether we are looking straight down at a fast piece of material or whether we are seeing it move away from us. I also showed you how relativistic flows of material can fool us about their speed. They can give us an optical illusion that they are actually going faster than the speed of light. Nothing beats the speed of light in reality, but it sure can look that way on the skies. And next week, I will talk about the most luminous explosions in the universe, called gamma ray bursts, and all the relativity that goes into understanding them. Thank you.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.